Hello. Recently we have discussed about the structure of MOSFET. So today we will discuss about the working of MOSFET. Okay, so let's make one heading, working of MOSFET. Okay, so first case we are taking when the VGS gate to source voltage equal to 0 and the VDS equal to 0. So let's draw the uh, MOSFET structure. Okay, and it is like this n plus p plus k. Now the VGS is equal to 0. Okay, and VDS is also 0. Since this VGS and VDS, since VGS equal to 0, then there will be no charge formation here. Okay, so though there will be no charge formation here also. Okay, no charge will form here. So there will be no current. So ID equal to 0 since no charge formed in channel. Okay. Now the second point is the second case we are taking when VGS greater than 0 but VGS is less than VTH and VTS equal to 0. So in this case, let's make again the diagram. So, okay, now there I'm giving VGS less than VTH. Okay, and there is N plus, and this. So what will happen? Uh, the hole will um, the hole will be repelled from here. Okay, and negative ion will form near to the surface of the dielectric, and these negative ions, uh, these negative ions are immobile, right? So there will be no current. So in this case also ID equal to ID equal to 0. Okay. So let's take another page and let's take the third case. In third case, VGS is greater than VTH and VDS equal to 0. Let's make again the structure of MOSFET. Okay, this is dielectric, then the gate will come. Okay, so we are giving here VGS, which is there. So center in we can make VGS greater than VTH, right? And VDS equal to 0. So since VGS equal greater than VTH, so there will be the formation of negative charge, free negative charge carrier, and these negative charge carrier will come uh, from im- the minority charge carrier from P substrate. Okay, from minority or from the this source or drain. Okay, from those two places it will come. This free negative charge carrier. See, Now negative charge carrier are there, those are free, but these negative charge carrier won't flow. So their ID, the drain current is zero. Still it is zero. So for ID not equal to zero, we must have to apply some voltage. So the current electron can start flowing and ID will come into the picture. So let's take the fourth case. Case number 4, when VGS is greater than VTH and VDS is not equal to 0. Okay, I mean VDS is greater than 0. Right, so let's make again one structure of MOSFET. Okay, this is P substrate. Okay, and then there is dielectric. This one is dielectric, and this one is gate. Okay, and these are source and this drain. Okay, so this is VGS, which is greater than VTH, and this is source voltage. We can keep it 0, and this one is VDS, so VDS greater than 0. Now because of this gate voltage, some positive charge will come here, and because of this, some free electron charge carrier will create in the channel. Okay, this is called channel. Okay, now because of this VDS, this electron will be attracted and this will start flowing in this direction. Okay, there will be one electric field because of this VDS, and the electron will start flowing to this direction. Okay, and there will be a flow of current ID in the opposite direction. So in this case, ID is not equal to 0. Okay, there is some drain current. ID means drain current. Okay, there is some drain current. So we saw three cases for this fourth case. In all those cases, the MOSFET was off. So in this case, MOSFET is on. Okay, so this is the working of MOSFET. So let's go to the next page and to the another concept. So let's take a fine pen, and the color is this one we can take. Okay, so this is a MOSFET. I'm making a MOSFET structure. Okay, and this is dielectric gate voltage, and it is VGS is greater than VTH and plus source voltage 0, and this is, oh sorry, there is one voltage VDS. So because of the VGS, some free charge will be created here, and because of this VDS, is electron will flow in this direction and current will flow in this direction. This is P subtrate. Okay, let's rub this. Okay, so what next? What I want to tell you, Like there is a potential difference between, where is my pen? Yeah, there is some potential difference. Okay, there, there, there. Okay, so if this VDS, first I'm considering VDS equal to 0. Okay, so the potential difference, so see there is a VGS voltage there. Okay, so there will be the difference of potential voltage between this will be VGS only. Okay, so now in second case, what I'm considering, okay, let me make it the picture again, one clear pic. Oh, sorry. Mm, okay, so yeah, there is electrons, there are electrons. Okay, and now I'm saying that I'm applying VDS voltage. Okay, so okay, this is VDS voltage. So see, because of this VDS voltage, there will be more potential here as compared to here and here. Okay, so the lowest potential will be there because of this VDS. Okay, and it will increase from here to here. Okay, right. So what will happen? So let here see the potential voltage is increasing from 0 to L. Okay, so what will happen? The potential difference between gate and this channel will also reduce since this is increasing. Okay, so let's consider here it is 1, here it is 1.5, then 2, 2.5, 3, and I'm giving here 5 volt. Okay, so there it will be 4. The potential difference will be 4. Then it will be what it will be? 3.5, then 3, right? Like so on. So the potential difference is in decreasing. Okay, so what we understood from here that when we applied this VDS, okay, so the potential difference is varying as we are moving from 0 to L. Okay, 0 to L. It is decreasing. See, so let's consider here it is 5, then 4.5, then the potential difference we are thinking, okay, just we are considering, and then 4, 3.5, 3, 2, okay, like this. So see, the potential difference here is the maximum, so it will attract more free electrons here, right? As compared to here, because the potential difference here is less, and so on. So like this. Okay, so you can see that the concentration of free electrons is decreasing as we are moving from 0 to L. So it will be like somewhat like this. Okay, somewhat like this. Okay, let me make one better picture. Okay, so let's go to the next page. Yeah, this one. Okay, so yeah, this is N plus. This one is N plus. Hmm. And this is gate. this is VDS and there is VGS. Okay, yeah. So we saw the concentration of electron will reduce. Okay, so we can say the concentration is maximum here and it will reduce like this. Okay, so there the electrons are more as compared to here, compared to here, as compared to here. Okay, so this is one observation. If we are applying the VDS, so the charge carrier concentration which will reduce from 0 to L. This is called channel length. Okay, this much. This is channel length. Okay, so this we understood. Now we want to see the impact on ID. So the next heading is yeah, impact on ID by different parameters. Okay, yeah. So first parameter I'm taking VGS. How VGS will impact the ID? See, easily you can think like VGS is if VGS is high, okay, then the charge Q will increase, channel charge, okay, will increase. Since charge increase, then ID will increase. Okay. Now the second observation is VDS. If VDS increase, how it will happen? Okay. See, since charge accumulated is like a resistance, okay, then by increasing VDS, that is increasing voltage across it, ID will increase. See, this charge is like I'm making figure here. This charge there, it is like a resistance. Okay, and I am applying one voltage across it, which is VDS. Okay, it is like this. This is VDS. So if I am increasing, this is let's consider R. If I am increasing VDS, what will happen? Simple. I will increase. This ID will increase. Okay, ID will increase. Okay, so we can say if VDS increase, then ID will increase. That is the second. Now the third, I'm writing on top. TOX. What is TOX? TOX is the thickness of this oxide layer. Okay. So if this TOX will reduce, then more charge carrier will come in channel. Okay. So ID will increase. So TOX decrease. Okay. Then this ID will increase. Okay. So now next is fourth. Fourth is width. Width means this. This is the 3D picture. So this is width. Okay. This is width. If W will increase, then also the charge will increase. Okay, this channel charge will increase. Channel, sorry. Because the channel charge increasing, so ID will increase. Simple. Okay. So four parameter, four impact we, four parameter impact we saw on the ID. So till now what we observed, what we saw, The first thing was the working of MOSFET. We saw the working of MOSFET. Second, we saw mm, impact of VDS on Q channel charge. Okay, so we saw that channel charge is, if I'm saying it Q channel and calling it X, so at 0 the Q charge was maximum and then it was reducing. Okay, like this we can say. And then we saw the impact on ID by different parameter. Next, next is the topic is derivation of ID current. Okay, so to calculate the current ID, which is the drain current. Okay, let's make one heading. Let me take thin pen, one fine pen. Okay, so ID derivation. ID derivation. Hmm. So first we will calculate the channel charge density. What is the charge density in channel? Okay, in MOSFET density. So we are taking case one. The case one is when VGS greater than VTH, but VDS equal to 0. So what will be the Q channel? Means what will be the charge in channel? Okay, that we have to see. So we know that this MOSFET is like a capacitance. Okay, this is dielectric. Okay, and this is P substrate and this is metal. So it's like a capacitance. So the Q will be CV. Okay, and CV can say Cox and area. Okay, Cox is what? Cox is farad per meter square. Okay, so Q channel equal to what is C? C is Cox A. Okay, and in case let me make one figure of MOSFET again. So okay, so there is this is the 3D picture. Okay, so this is W and this is L. Okay, so the area will be W into L, right? So it will be Cox dot W dot L. Now we need V. So what is V? The gate voltage which we are giving. VGS. So dot VGS. Is it correct? No. So if VGS is equal to 0, see when the channel charge will come. When VGS is greater than VTH. That is the condition for making the free charge carrier in channel. So that's why if you are taking VGS then charge the channel charge will be equal to 0, then we won't know. So better we should use something else. If VGS equal to VGS, that time also the channel charge will be 0. So we can use VGS minus VTH. Okay. So this is a channel charge that we got. Okay. So this is the one equation. Okay. And one more thing, we can see the charge density, I mean charge per length. Okay, so it will be COX W VGS minus VH, and we can call it Q channel density. Okay, now let's go to the next page. This is our first equation. Okay, now we are taking case 1. In the first case, we took VGS greater than VTH, but VD 0. In second case, I am taking VGS greater than VTH and VDS not equal to 0. It is greater than 0. Okay. So what will be the uh, channel charge density? Previously, it was when the VDS was not there, it was WCOX VGS minus VTH. Is it okay with this case also? Let's see. So let's make again the MOSFET diagram. So yeah, okay, okay, this, okay, and there is VGS which is greater than VTH, and I'm keeping here VDS. Okay, this is N plus from charge. Okay, so now, mm, okay, see on this side, that we are calling it point A. Okay, this one point A, this one point B. So at A to B, here the mm, there will be no impact of VDS, right? We're at A because and the charge, see, Q channel, it will reduce like this. So see, this charge concentration will reduce from 0 to L, right? This is L, this is 0, 0 to L. Okay, so you can see it's not constant. It's not only depending on VGS anymore, it is depending on VDS also. So it is reducing. So this equation is not applicable in this case. If we are talking about this particular place, let me take one another pen. This pink I'm taking. Yeah, this small length I'm taking. So this charge concentration won't be equal to this much or to this. Okay, so this equation is not applicable. So we have to take something else. So let's consider here in this small length delta L, the voltage is Vx. We can take. This is this is x distance. Okay, from 0. It is x distance. Let me take one another pen. Red one I'm taking. This one is x distance. Okay, and there the voltage is Vx that I'm considering. So the we have to take equation Q channel density equal to WCOX VGS minus VTH as well as Vx. Okay, so this is applicable here or here, here, here. At this point only, when the VDS is not equal to 0, then only this first equation is applicable. So now we have to use this second equation. But see what we want to calculate. We want to calculate the drain current. Okay, so how can we calculate that? Let me take razor. Mm, okay, let me remove all this thing. Okay, yeah. So which pen, blue pen I'm taking? It is why it is not coming? Shit. Okay, let me take this. Okay, so I want to calculate ID. Since CVOS, we saw that in MOSFET, if I'm making a gain, there I was giving some VDS voltage because of which electric field was generated here, and because of this electric field, sorry, because of this electric field, electrons were start moving in this direction. Okay, okay. Let me take different pen. This black pen. Okay, so electron were moving in this direction because of this electric field, and this was the drift velocity of electron. Okay, this is called drift velocity. The electrons are drifting, but what velocity? That is called drift velocity. And the drift velocity is equal to uh, mu n, since we are talking about electron. Okay, so mu n e. This is drift velocity equal to mu n e. And see, the velocity is equal to uh, dx by dt also. Okay, for a small distance we are looking. So it is dx by dt. And we know that uh, mm, e, that is equal to minus dv by dx. Okay, now, so what can we do? Let's put this equation there. So Vd will become equal to mu n e. E will become, okay, sorry. E is dv by dx. Okay, minus. And what voltage we were considering on this dx point? Vx, right? So we can say like this. Okay, now next page we can go. Me Let me write the formula previous. What was that? Yeah. Mhm. Okay. Vd equal to minus mu n dvx divided by dx, or we can say dx by dt. Okay, that we can say. Now, what is id? What is I? Formula of I. I is equal to dq by dt, or we can say it dq by dx and dx by dt. We can say that. What is this? This is nothing which we calculated already, the charge concentration. What was the value? That was this. See, the charge is negative. Okay, so we have to keep it negative only. Okay, so this is minus w mu n, and then there was VGS minus VTH and Vx. What is multiplication of it? Multiplication of it it is okay. We can keep it like this, mu n dot dvx by dx. Okay, yeah. So, oh, sorry, little up, yeah. So now id, what we can say id dot dx. This dx, let me use another pen. This dx, we can take to the id, okay, like this, and it will be equal to minus minus will become plus, this minus and this minus. So it will become mu n w. Okay, there was cox also, sorry. There was cox also, mu n w cox vgs minus vth minus vx, and what is there? dvx. Okay, now we have to calculate the id. For that we have to integrate it, and here we have to integrate it from 0 to L, since in MOSFET we are looking from here to here, and that was 0 and this was L. Okay, so that's why 0 to L, and here we will look 0 to VDS, because here the voltage is 0 and there it is the maximum VDS. Okay, so now let's start doing the integration. So it will be mu n w cox, and then vgs minus vth dvx integration by 0 to vds, and then minus vx dot dvx, and this is integration by 0 to vds, and here it will become id dot l, right? The integration of this will be x, then l minus 0 will be l. Okay, so id will equal to mu n cox w by l. This l will go there. Okay, and into this will be vgs minus vth, and it will become vds minus 0, this one. So it will become vds. Okay, and minus this will become v square x. So we have to minus this. So it will become vds square by 2. Okay, so this is the equation of the drain current of MOSFET. Okay, so I'm writing again this equation. I'm using a bit thick pen now. So ID equal to mu n cox w by l vgs minus vth, then vds minus vds square divided by 2. This is the equation, okay, of drain current. Easy. It is very easy. Now let's see the impact of VGS on ID. Sorry, impact on ID. Hmm. So let's make graph. This is VGS and this is ID. So when the VGS is equal to 0, what will be the ID? It will be 0. So when ID will start, we are first of all, see, we are considering VDS greater than 0. Okay. and up to there is VTH. Okay, so up to VTH there will be no current, it is zero. And then when it will become VTH, it will start increasing like this. Okay, so this is the uh, waveform of I, the impact on ID of VGS. Okay, so in this lecture, only this we will see. Rest we will see in the next lecture. Mm, yeah. So in this lecture, we have covered in the working of MOSFET visa, then visa mm, uh, parameters which impact ID and how they are impacting. Then we saw ID derivation. Okay, then we saw the charge concentration, dependency on VDS. These we have observed. So in next lecture we will see the characteristics waveform of MOSFET and some other important topics in MOSFET. Okay, yeah. So thank you very much. Bye.